Okay, this video is to help explain how to talk about the force of gravity on an inclined plane. Now, this is relevant for the BC investigation about the pass cars accelerating. And if you're thinking about trying to explain what are the forces acting upon this pass car as it's moving on a ramp down at an angle. So that's our inclined plane. So this box here represents our pass car, and this triangle that I've drawn represents the ramp that we're going to slide the pass cars down. And this is at an angle. I've made it at a 30-degree angle just because it's a simpler angle, simple numbers to talk about. And the right angle could be, created by stacking a bunch of books, and that's what's holding up the ramp. Okay, so what forces are acting upon the pass car? Let's try to change color here. Okay, so we know that there's a force of gravity. The force of gravity always pulls down. So this is Fg. We know that there's going to be a normal force that's perpendicular to the surface, and we know there's going to be some kind of drag, some kind of friction pulling backwards. We also know that the car is going to start rolling down the ramp. It's going to start accelerating down the ramp, so there must be some kind of net force that's going down and to the left down this ramp. So how does that work? So we're going to focus in on the force of gravity, and it's pulling straight down, but we can actually break down that force into sort of two components, we say. So if I change my color again, there we go, I'll make it red. So it ends up acting, the force of gravity, like it's actually forces in two directions. So we say there's one component that's pulling sort of down this way, and there's a component that's pulling down this way. And you see it kind of works out, it makes this nice right triangle once again. Okay, so let's see, we've got the force, I'll say for now perpendicular. I can use this funny little perpendicular symbol. And then I can say this one is the force that is parallel. So it's parallel to the ramp. Okay, so now we have to bring in some trigonometry. And maybe I should have drawn my triangle better, but I think we'll figure it out. So if this is a 30-degree angle, and I think of this gravity arrow is going all the way down here to make a right triangle, then what is this angle here? This angle here has to be 60 because all the angles in the triangle have to add up to 180. Okay, well, if this angle is 60, and if this red line down here is a right angle, again, this is, it's perpendicular, right? With the normal force, it's always perpendicular to the surface right there. That's 90. Well, if this is 60 of that, then the angle in here must be 30. So let me clear out some of this space and zoom in on that. So this angle is, there goes, let's undo that. Let's make my eraser a heck of a lot smaller. There we go. Let's try that again. So if I just take away that little right angle, there we go. So this angle inside of the triangle must be 30 degrees to add up with our 60 to 90, and I can see there's a right angle right here. Okay, so that angle is going to be important. Basically what we've got here is we've got some trigonometry. So for those of you that have done some trigonometry, this is where this is an example where it's going to be applied in science. So when we have a right triangle, we're trying to figure out what is this component of gravity, the one that's parallel, versus the one here that is perpendicular. That's the perpendicular one. So let's we can maybe redraw our triangle down here and look at what we're dealing with. So the one, ooh, that was ugly. Okay, let's try that again. The one that's straight down is the force of gravity. Okay, and we can calculate what the force of gravity is because that's an object's weight. That's its mass, whatever its mass is, times the acceleration of gravity, 9.81 meters per second squared. So Fg I can calculate. Then I've got my component this way. I've got my component that way. These are the two things I'm trying to solve for. Perpendicular. This is a 30-degree angle. This is a right angle. And this must be a 60-degree angle. Okay, so if we know our trigonometric functions, then we know that the sine of an angle is equal to, sine of theta, is equal to the opposite over the hypotenuse. So if I think about this 30-degree angle, then the opposite side is the parallel force, and the hypotenuse is gravity. That's the long side of the triangle. So depending on what I'm trying to solve for, if I know the angle is 30, for example, and if I know the mass and I know the acceleration, so let's say the force of gravity is 10 newtons, just to keep it a nice easy number. When I do this, I can solve for my force parallel. So I can get that the Fg times the sine of theta equals the force that is parallel. And so now if I plugged in numbers, I've got force of gravity that's 10 newtons. That's the weight of the pass car, made up weight. And then I have the sine of 30 degrees. And whatever that is, that's going to be the force of gravity that's actually pulling down the ramp in the direction of the acceleration. Now the sine of 30, if you punch that into your calculator, if you memorized it, it turns out equals 1/2. And so in the end, I can see that there is a force pulling down to the left of 5 newtons. So this is the force that's actually causing the net force and is causing the acceleration. Now I'm not going to get the full 5 newtons downwards as my causing my acceleration, because I know there's a force of friction pulling back up, but it's this force parallel, which is greater than the force of friction, and that's where we're getting our net force. There's some kind of net force that's in this direction and causing the acceleration. Okay, well, just in case we wanted to, how would we calculate for this perpendicular component here? Let me switch colors. We will go green. Okay, so this one here is the one into the ramp. Okay, that's this force that is perpendicular. Okay, well that, according to this triangle, is the adjacent side to the 30-degree angle. So then I'm going to use the cosine. The cosine of theta, of an angle, is the adjacent side over the hypotenuse. Well, in this example, the adjacent side, like I said, is this perpendicular part of the force, and the hypotenuse, once again, is gravity. And so now if I solve for that, I get this, and if I plug in those numbers, 10 newtons for the weight, cosine of 30 ends up being 0.86, and so the force into the ramp is 8.6 newtons, so that's the force going this way. And so now we actually know what the normal force is, because we know that the normal force is the force that pushes out from the ramp. And so if we draw it again, so here's my triangle, probably not at all a 30-degree angle, but forgive me. Here's our car again, and we've got Fg down is 10 newtons. This one going out is 8.6 newtons. And really the force of friction is the one that we don't actually know right now. If I fill in other colors, we figured out that the force into the ramp from that cosine calculation is also 8.6 newtons. So we see that there's no net force up out of the ramp or down into the ramp. They're canceling. And we can see that there's 5 newtons traveling downhill this way. And so it's really these two together, that there's a net force going down and to the left, and that's what's causing the acceleration. And based on the acceleration, we could figure out the resultant force, and we could try to solve for the force of friction as well. But that's how you can use trigonometry to actually calculate the different components of the force of gravity to work with figuring out the resultant force down the ramp.